the Labflow workshop and welcome to the experiment number 9 in Labflow. Today we will investigate the experiment reactions of hydrocarbons. We are starting to study organic chemistry. So what are hydrocarbons? Hydrocarbons are organic compounds that contain only carbon and hydrogen. They are, in general, flammable. So you know, by experience, we cannot handle hydrocarbons near open flames. We usually work inside a fume hood. Another characteristic of the hydrocarbons is that they are non-polar compounds. What does that mean? That they are not soluble in water. We will see some examples later. So the first division that is doing in this background, in this write-up of the experiment, is the division that hydrocarbons can be either saturated or unsaturated. In the examples of the write-up, let me see if I can. In these examples that are shown here, we see that the carbon atoms in saturated hydrocarbons, this is a saturated hydrocarbon, have all 4 single bonds. And unsaturated hydrocarbons have at least 2 carbons with double or triple bonds. These are unsaturated hydrocarbons. So let me share a whiteboard to show you what I am talking about. So in the example as written here, the only unsaturated carbon compound that is written here is written like this. And this is the example that they are giving us for a saturated hydrocarbon. What I want you to see is the way they write here. You have to know that it's easy to remember that carbon has valence 4, right? So it's going to be saturated, and they are called alkanes when the carbon, let me write this compound in a different way. Instead of writing CH3, remember that carbon has 4 bonds. 3 are bound to hydrogen, and the 4th bond is bound to another carbon. And then this carbon, they write H2, but actually carbon always have to have 4 if it is a saturated hydrocarbon. So, and the bonds are always going to be single. And then we do the same thing. I don't have more room, but the carbon has to have 4. So what I will do is another CH2. So this, let me write it here. These 2 are these two. And then, instead of writing CH3, I write it this way. All I want to show you is that if a carbon has its bond to 4 different atoms or the same atom but has 4 bonds and 4 single bonds, and all the compounds, all the carbons have single bonds, okay, easy peasy, it's actually a saturated hydrocarbons, and they are called alkanes. Alkanes. Just to start. So it shouldn't be any confusion of saturated or unsaturated. Now, let's look at the unsaturated examples that they are giving here in the write-up. The first one is this one. Instead of writing CH3, I will do this. And carbon always have to have 4. Remember that, because that will help you in identifying the saturated or unsaturated hydrocarbon. So in this case, when we look at this compound, what do we see? Of course, all the carbons have to have 4 bonds, but these 2 carbons have a double bond. When in the compound you have at least 1 double bond, you have an unsaturated hydrocarbon, and also they are called alkenes. And then what happens when we have a triple bond? They are giving us another example. 1, 2, 3. This is a triple bond. 1, 2, 3. And carbon in total has to have 4. So this is not exactly the example that they are giving us, but this has a triple bond. So this is called, because it has a triple bond, is called an alkyne. This is an alkyne. So when you are in the presence of a compound and 2 carbons have at least a triple bond, you are going to say it's unsaturated and it's an alkyne. And this one, when you see, it's also unsaturated because 2 carbons have a double bond. And these compounds, when you found that the compound have at least 1 double bond, they are called alkenes. So this is the first division, and basically this is simple that they are doing with hydrocarbons. They are dividing or classifying the hydrocarbons between saturated and unsaturated. And the saturated are easy to pick. They are alkanes that all the bonds are single. 1, 1, 1. Not like here, that 2 carbons are bound together with a triple bond. And here, two carbons are bound together with a double bond. And that is the first division. And then there is another type of unsaturated hydrocarbons. And those are the aromatics. So we saw, and here in the example in the write-up, they are giving us unsaturated hydrocarbons. They are giving an example of an alkene, one example of an alkyne, and the third example, let me see if I can go down. No, I will erase this. And the third example is an aromatic. This is an aromatic. I can write it in a different way to make it easy. Always see that the carbon has to have valence 4. 4 bonds, right? So now, what happens in the aromatics, there are rings that have alternating double bonds. So double bond, double bond, double bond. And then because we know that the carbon has to have valence 4, we have to complete this with hydrogen. So let's look at this carbon. This carbon has to have 4. So 1, 2, 3, the rest is 1 hydrogen, always completed with a hydrogen. When they draw the aromatic in this way, they assume that we know all this, but I'm writing it so you know what is the structure. And that will happen with all the carbons. This carbon has 1 double bond and 1 single. So 1, 2, 3, 1 more hydrogen. And that will happen with all of them. So this is the structure of benzene. And why is this aromatic? We said, and this is another type of unsaturated hydrocarbon. And they basically behave different from alkenes and alkynes. And we said that they have alternating double bond. And one characteristic of the aromatics is that these alternating double bonds are stabilized by resonance. What does that mean? You will hear that, oh, the aromatics are stabilized by resonance. What does that mean? That means that the electrons, in reality, I draw benzene like that, but constantly the electrons are delocalized. So basically, this is called a pi bond. One is a sigma bond, which is the first single bond, and the other is a pi bond. So the double bonds are basically alternating in the ring, which means this goes here, this goes here, and this goes here. So I draw one, and then you only have to be able to do this. You are not in organic chemistry. So what you are going to do, I will do this so you know. I only want to show you that the resonance means that if the double bond is here, see this arrow is moving here, and then all are moving. So basically, to make it a little simpler, the resonance, you can do this now that you know the real structure. And when they ask you the resonance, you do an arrow like that, pointing both ways. And all you have to do is show that you know that if the double bond in this one was here, it's going to move. What does that mean? That it's moving. It's basically the electrons are delocalized, are actually moving inside this ring. And sometimes you will see the benzene written like that, with a circle inside. And that means that the electrons are stabilized by resonance. Benzene and all the aromatics are very stable compounds because of that resonance. The double bonds have those resonance position, and the electron density is spreading from the double bond around the whole thing. With that concept, I don't think you need to know much more. But yes, that aromatics are unsaturated hydrocarbons that are stabilized by resonance. That is important. That means even though they are unsaturated, the reactions that you will see or the qualitative analysis that we will see in this experiment will be different from the alkenes or alkynes, even though they are, all of them are unsaturated hydrocarbons. But the benzene is much more stable. So the resonance of the double bonds prevent them from producing addition reactions. So let's see what is an addition reaction. I will clear this, and in the write-up we will go over later. There are one test that we are going to do today is testing for unsaturation. So let's say, remember that carbon has to have four valence, four bonds. In this case, you see a double bond. What does that mean? It's unsaturated, and because it's a double bond, it's an alkene. And we know, we will go over later, that if you want to differentiate, to find out if you have a saturated hydrocarbon or unsaturated hydrocarbon, you will do the bromine test. This is actually a bromine. And what is this is something you have to remember, the reaction, but it's not difficult to remember. When you see a double bond, this double bond is much easier to break than a single bond. Much easier to break. So this pi bond will perform an addition reaction. So when we add in the test, we add bromine. This has a color depend, can be orange if it's diluted, can be a yellow, a solution you can see yellow. And then once you put them together, you put a few drops of bromine, what is going to happen? This bond break and is going to form a new one here. Instead of these two red connected in the pi bond, it's opening. And here it is, the addition of bromine. And the rest is the same. This carbon was bound to two hydrogens, they stay. The only difference is the addition these bonds, double bonds, are easy to break, and here we see. So that means if the color was originally yellow, we will see no color because we don't have any more bromine. The bromine is part of the compound. So this all, we will go over this very soon, but I wanted to share with you that unsaturated hydrocarbons will test positive with the bromine test, but aromatic compounds are not that easier to react because the resonance that we just mentioned of those double bonds, that they are all together, prevent them from producing addition reactions like alkenes or alkynes. They do substitutions reaction, but it's not the point in this experiment for non-majors. And let me share the page of the experiment before we do practice problem, and then we will go to see the report and make sure you know how to complete your report. Let me share the application again. Okay, okay. Okay. So we saw from the write-up, I'm going through the write-up, we saw aromaticity. This is what the benzene, I was talking about the resonance, and because of the resonance, sometimes they write the benzene with a circle inside. And then here is talking about okay, sources of hydrocarbons. Okay, in this part, all they are saying that even though the hydrocarbons are obtained from oils or fossil fuels or natural sources in general, they can be prepared in the lab. So in this experiment, we will prepare ethane that is called acetylene, that is carbon 2, hydrogen 2, from calcium carbide. All we are going to do here is add water to the calcium carbide, and we will see the acetylene. And because it's a gas, we will see bubbles. So in this experiment, we will do the preparation of acetylene, and we will perform 2 qualitative tests. So it's actually, this experiment is very simple. I'm just giving you an overview, so then it's clear when you have to do your quiz and your report. So we said that in this experiment, we will perform just 2 qualitative tests for hydrocarbons. But I'm asking you, what are qualitative tests? Well, they are chemical reactions that will give you a visual change when the reaction is positive. And different classes of hydrocarbons will have different reactivity. So we use the qualitative tests to differentiate, and they allow us to distinguish what type of hydrocarbons we have. Because we are doing just 2 tests, you only have to memorize or remember what is a positive and a negative for each tests, but they are only two. For example, the first test here, bromine test. This is what I was showing right before. So the bromine test is to find if you are in the presence of an alkene or an alkyne. So remember, you want to know if you have a double bond or a triple bond, but not an aromatic, only a double bond or a triple bond. So bromine will react with aromatics, but with much in a different pathway. It requires a catalyst. For the purpose of this reaction, it will be a negative. So if the test is positive, you will know that you have either a double bond or a triple bond, which means you have an alkene or an alkyne. In this case, it says reaction observed in a positive bromine test with alkene. This is an alkene because it has a double bond. So I started, you will watch actually the two videos that Labflow is offering. So then you will be able to see the difference in color. You add a drop of a yellow and the yellow disappears if the reaction is positive. If the reaction is negative, nothing happens. The yellow stays, and you will see the video. And then here they're saying that they will do what they are. This is a little confusing because they are telling you that aromatic react with bromine, but not in the conditions that we are doing the experiment. That's why I don't know why they wrote it here in this way, because in order to be positive, in general, aromatics won't give us an addition reaction. If you see here, you still have the double bond. This is called a substitution reaction. It's completely different than the one that I show you, that the double bond broke, opened up, and two bromine atoms were addition to the molecule. In this case, the pi bond is still there. So this is called substitution, and you need a catalyst and you need different conditions. So for the purpose of our tests, aromatics are negative. That's why I think this reaction is confusing here, but because it's here, we talk about it. And then potassium permanganate, that's the second test. Again, this is another test we are performing in today's experiment. And what are we testing? We want to know if we have an alkene or an alkyne, same way that before. In the previous reaction, you see the pi bond disappears and two bromine atoms are additioned to this carbon. And in the reaction of permanganate, right here, of course, the pi bond is broken, but instead of two bromines, you see two OH, and the permanganate originally is purple. So you add a few drops of a purple solution, and then what happens? You will see a brown precipitate of magnesium dioxide. And if that happens, if the color purple changes to brown, that means that the reaction is positive. And when are you going to have a positive reaction? Only with alkenes and alkynes, only with double bonds or triple bonds. So now, and this is also called Bayer's test. So any questions so far before we go to do some practice problems. Okay, so the first question, what is a saturated hydrocarbon? What is a saturated hydrocarbon? We went over, we said that hydrocarbons are organic compounds that contain only carbon and hydrogen. And in saturated hydrocarbons, all the carbon atoms have 4 single bonds, which means if I have a saturated hydrocarbon, the compound will have all single bonds, and that is a saturated hydrocarbon. And what is an unsaturated hydrocarbon? Unsaturated hydrocarbons have at least 2 carbons with double or triple bonds. Right? So is this compound saturated or unsaturated? This compound is unsaturated. It's an alkene because it has a double bond. Let's look at these examples. It says, which of the following compounds are unsaturated compounds? And identify if each type of hydrocarbon, if it's an alkane, if it's an alkene, if it's an alkyne, or an aromatic. So let's look at the first one. A. Is this an unsaturated or saturated? You can message me. A. Is an unsaturated compound or saturated compound? You see that this is the same as a triple bond so it's unsaturated and it's an alkyne. Look at B. B has all single bonds, no double, so it's a saturated alkane. Look at C. We said that it's an aromatic ring and it's an unsaturated compound. Why? Because we said that aromatics are rings that have alternating double bonds that are stabilized by resonance. So this is an aromatic. And it's unsaturated. How about the last one? D. They're all single bonds. So it's an alkane and it's a saturated compound. This compound is cyclohexane. It doesn't matter that it is a cycloalkane. Still, when you look at the carbons, there are no double or triple bonds. So it's going to be a saturated alkane. And let's look at the next question. It says, in general, are hydrocarbons soluble in water. Why? What do you think? Hydrocarbons are non-polar compounds, we said at the beginning, and water is polar. For that reason, we know hydrocarbons do not mix with water. So we say that like dissolves like, meaning that substance with similar chemical characteristics will dissolve in each other. So polar solvents dissolve polar solutes, and non-polar solvents dissolve non-polar solutes. So what is the answer? Non-polar and polar substances are immiscible. They do not mix. So you know that hydrocarbons won't mix with water. And then the last question is, why is it better to handle hydrocarbons in the hood? Many hydrocarbons are flammable. That's why we need to work inside the hood, the fume hood, to contain the vapors. Any questions here before we go to share the report? Let's look at the sample data. When you look at your report that you have to complete, the first part of the report is going to ask you if if your compounds, alkane, alkene, and the aromatics are soluble in water. So by observing this data, what do you see? Water is in the bottom and the alkane is in the top. Are they soluble? Obviously not, because they have two phases. And you will have to write which one is the top layer. Just by looking at this data, you will know if it's which one is the top layer and which one is the bottom layer. And then you will have an unknown that you will have to decide what is it. And then you will have to complete by looking at this data. You will have to complete if you have a positive or a negative with a bromine test. So if you look at here, you add bromine that is a little orange or a little can be yellow as well. So you will have to know if you did the reaction with an alkane and you see that the color is yellow. We said that if it stays yellow, the reaction is negative, which means that the alkanes are testing negative with the bromine test. But we said that if the reaction is positive, the yellow color disappears. So we have alkene that the reaction is positive. Let's continue looking. We look at aromatic and we said that the reaction is negative because it stays yellow. And the same way you are going to complete. And then you will have to complete the permanganate test for double bonds. So the permanganate is purple. So you are going to add, it will be the same thing. If the purple stays, the reaction is negative. If the reaction is positive, so the alkane is giving us a negative. But here you see the brown color of the of the manganese dioxide. This is brown color, so the reaction is positive. So we see that alkenes give a positive reaction. In the aromatics, I believe, talk to your instructor. I think in this picture, there is a mistake. According to this picture, the reaction is positive, but aromatics do not give a positive reaction in these conditions, just adding a drop. So if you go with the picture, the reaction is positive. But as I said before, aromatics and alkanes give a negative reaction. And this is the data. Let me see if there is something else, so we can go and share the report and see if there is something else that we need to look at. Okay, so this is a similar report that you are going to see. The first part, we went over the solubility, so you will look at the data. The bromine test we went over. It will be easy just to complete this and then compare to your unknown. And then the formation of ethine. It says, what did you observe that suggested a reaction with the formation of ethine? We said that ethine, which is this compound, we said that this is a gas. So when you see a gas, when you are in the presence of a gas, you always see bubbles. And then they are asking to draw the structure of ethine, which is this compound. And I believe this is a very simple experiment. There are a few questions after that. Are hydrocarbons soluble or insoluble in water? Okay, obviously you saw the two phases, and it says which hydrocarbon group is the least reactive and why. And you saw that we mentioned that alkanes are harder to break. Single bonds are harder to break. So they are actually the least reactive because they don't have double or triple bonds. And then they ask you for the balanced equation that of the reaction that you are performing. That is the calcium carbide that is a solid and reacts with water to form calcium hydroxide plus the ethine that is a gas. And this is the chemical reaction. What else is asking us? Okay, it says how many grams of acetylene would be given off if the limiting reagent in the reaction is calcium carbide, and you start with 2 grams. So we saw in the reaction that I just wrote that you have with 1 mole of calcium carbide, you will form 1 mole of acetylene. So all you have to do is you start basically with 2 grams. You start with 2 grams of calcium carbide. But you know, in a chemical reaction, you always have to convert into moles. You can never work with grams. And they are giving you up here the molar mass of the calcium carbide. So you know that 1 mole of calcium carbide equals 64.1 grams of calcium carbide. So what I did so far is convert the grams of calcium carbide into moles of calcium carbide. But what are they asking? They want to know the grams of acetylene. So now I have to work with the molar ratio. You know that 1 mole of acetylene comes from 1 mole of calcium carbide. The ratio is 1 to 1. So now when I cancel the units, moles of calcium carbide and moles of, my units are moles of acetylene, but they are not asking for that. They say how many grams. So all I have to do when I have moles of acetylene to convert into grams of acetylene is just one more step using the molar mass. I know that 26.0 grams of acetylene equals 1 mole of acetylene. This is the molar mass that is given here. When I do all those calculations, I end up with an answer. You can plug in all the numbers that are in the numerator, multiply everything in the numerator, and then divide by all the numbers in the denominator. And I think, let me see if there is something else here. It says in 5, draw the 2 resonance structures of benzene. That is what I wrote at the beginning, how the double bonds alternate. And I think I will conclude this workshop and stay in case you want to ask me questions. And thank you everybody for being here today.